Okay, so let us continue with our discussion of the universal covering. So what we have gotten so far is that we have proved that the map P from X unit to X is a covering map. We have shown that it is we have also shown that X sub univ is locally arcwise connected, locally simply connected, basically because P is a local homeomorphism. And X has these properties. Okay, so we have proved that this is a covering map, and so X sub unit is of course locally arcwise connected, locally simply connected. The only thing that remains to prove is that X sub unit is actually arcwise connected, okay, globally arcwise connected, and we have to show that it is simply connected, okay, which is what we are going to do. All right, and then towards the end we would like to see why the fundamental group of X can be identified as subgroup of automorphisms of this universal covering. Okay, so so first let us try to prove that X sub unit is arcwise connected. Okay, so the key to that is the existence of very canonical lifting of a path starting at X to X unif. Okay, so it's in the following way. So given suppose I am given an alpha in X sub unif, so how is it going to look like? It's going to look like well, you know, so let me draw a diagram again. So here is my X, here is this point small x I have fixed, and in X sub unif I have this point alpha, and you know this alpha is just going to lie above the end point of the path alpha that starts from X and ends at alpha of 1, and this point is going to lie over this, namely it is going to be mapped to this under the map P, which goes from the universal covering space to X. Okay, now you see, and of course over X there is this path, that is a unique point Cx, okay, which is a constant path at X that gives me a point that lies over X. Okay, now I am going to do the following thing. What I am going to do is, you see, if after all, what is alpha? See, alpha is just a continuous map from I to X, okay, that sends a t to alpha of t. Okay, now I am going to do the following thing. Take any t in I, of course I is the closed interval 0 1, the closed unit interval on the real line. Okay, take a t, then I am going to get a point here, namely alpha of t. Okay, and I am going to do the following. I am just going to consider the path that starts at X at time t equal to 0 and at time t equal to 1 ends at alpha of t. Okay, so that you can believe is going to give me a point here which I would like to call as alpha sub t. Okay, and as t varies I will get a path above which is exactly lying over this path below, and this path above is what is going to be the unique lift of the path alpha. Okay, so this path above is going to be alpha tilde, that is the unique lift of the path alpha to the universal covering starting at this point. Okay, this point which corresponds to the constant path at x. Okay, so how do I write this down? So you see what I do is I define a path alpha tilde. So this is from I to the universal covering, and you know what this path is, it is just going to send S to well, let me put S is going to go to alpha sub S. Okay, and I am going to put this where alpha sub S is the path from x to alpha of S along alpha. Okay, so you see what is so you know this. Okay, there is a I have put in another variable S here, that is because of obvious reasons, because I will have to define this alpha sub S. Okay, so you know basically what is happening is that you see given so what I am actually doing is, you see I am just shrinking alpha along itself from alpha of 1 to alpha of 0 which is x. Okay, and this shrinking provides me naturally a homotopy of alpha with the constant path at x. Okay, and this homotopy shows up as a path above. Okay, so what is happening is, see, points above are paths below starting from x, and in fact the homotopy below is showing up as a path above. Okay, that is what is happening. So it is very easy to define alpha of S, it is not difficult to define alpha of S. It's so alpha sub S is the path which at time t is just alpha of st. So this is the path. So you see, you can see that when t is 0, you can see that when t is 0 you will get alpha 0. Okay, and when you will get alpha of 0 which is x. Okay, and when t is 1 you get alpha of S. Okay, so it is a path which starts at x and ends at alpha of S. Okay, so it will lie above this endpoint alpha of S, right. So and it is also clear that there is a multiplication of variables here which is continuous. So a little bit of work has to be done to show that this map alpha tilde is actually a continuous map. Okay, and once you establish that, what happens is that we see that given any alpha starting with x, okay, I am able to get a lift alpha tilde. That lift is unique, that is because you know the moment you have a local homeomorphism, the liftings are unique if you fix the initial point. Okay, and the lift is a path that connects this point alpha to this point Cx. Now you know if I had 2 points, okay, I can connect them by 2 paths to Cx, and therefore I can connect them to each other by a path. Okay, that will tell you that this space is arcwise connected. Okay, so a little work, a little exercise shows alpha tilde is continuous. Hence any point alpha in x sub univ can be connected to Cx by a path namely alpha tilde. So given any 2 points alpha and beta here in X sub univ, they can be connected by the path. Well, you know, I'll have to go. I have to shrink alpha. I have to shrink alpha to X, and then I have to unshrink. Beta. Okay, so so the path will be just you first apply alpha tilde. Okay, that alpha tilde will go from. So in fact I should take alpha tilde inverse because I want it to go like this, and then I will apply beta tilde. Okay, so this this path will do the job. All right. So this tells you that therefore this is arcwise connected. Okay, this tells you that this is arcwise connected. In fact, it tells you even more. What it tells you is that, you know, I told you that a covering space has the unique path lifting property. Okay, that was one of the consequences of the covering homotopy theorem. Okay, and but that in this case that this covering has the unique path lifting property. Okay, can be directly deduced from this construction. Okay, so this construction this also shows why P from has why this covering has the unique path lifting property. Okay, that also follows from this. Why? Because you see, of course I need not worry about the uniqueness. Okay, because the uniqueness will follow because it's a local homeomorphism once I have fixed the initial point. Okay, but why does this argument show that? Because you see, now you know. Okay, so let me draw. Maybe there isn't enough space here. I should go to the next board. So let me do that here. So I have, so here is my X. Okay, and suppose I am given a path from a point, let us say X prime to another point X double prime. Okay, and let me call this path as sigma. Okay, suppose sigma is a path on X, on capital X, from say X prime to X double prime. Okay, now so what is the path lifting property? Give me a path below and give me a point above. Okay, give me a point above the initial point. So that means I'm going to be given I have to start with an alpha which goes to this X prime. Okay, and I have to show that there is a lift of this path. Okay, now what I do is, well, you see, there is this path X, there is this point X, giving this alpha amounts to giving a path like this. Okay, and you see, now consider alpha followed by sigma. Okay, by this construction alpha followed by sigma has this lift which is literally got by shrinking alpha followed by sigma. Okay, and you can see that so that you can see that, you know, if this is the point Cx that is lying over X, okay, then you can see that the lift that I have constructed there of alpha followed by sigma will be this lift of alpha, namely alpha tilde that I have constructed there, followed by a certain other lift of sigma. Okay, so this will be sigma tilde, but this will be sigma tilde, the lift of sigma to yeah, with starting point alpha. Okay, so this will be sigma tilde sub alpha. Okay, so and then this piece is going to just be the lift of sigma. Okay, so let me write that down. The lift, the unique lift alpha sigma whole tilde, okay, which you get by shrinking sigma and then shrinking along alpha, that is going to be equal to I mean it has to pass through this point alpha, because at some point of time you are going to shrink it to alpha, okay, and therefore it has to lie here, okay, and so this will be alpha tilde followed by a sigma tilde sub alpha, where the sigma tilde sub alpha is the unique lift of sigma starting at alpha. Okay, so this construction also tells you that you can directly see the path lifting property. You can see the path lifting property just looking at this shrinking homotopy. Okay, and a similar argument will tell you that you can also lift homotopies of paths. Okay, so that's also something that's promised by the covering homotopy theorem, but that is something that you can directly see in this case. Okay, so similarly, so let me write that. Similarly, the homotopy lifting property for paths can be also directly seen from this construction. Okay, so that's also something that I can quickly explain for you. So basically if I have x here, okay, and so suppose I had suppose there are two paths in x, let's say alpha, and I have another point another path beta, okay, and suppose alpha and beta are homotopic, freely homotopic, okay, it's a free homotopy, which means endpoints need not be fixed, okay, suppose they are homotopic, then basically you will get a diagram like this, okay, which is the image of a map capital F, which is a homotopy from I cross I to x, and what will happen is if I call this as well t comma s, okay, then and if I call f sub if I call f of t comma s to be f sub t of s, okay, then saying that f is homotopy from alpha to beta is the same as saying that f sub 0 of s is alpha, beta is f sub 1 of s, okay, and so alpha is homotopic to beta via f, that is your homotopy, okay. Alright, so and mind you this is also going to be a path, okay, and this is also going to be a path. What is this path? this is going to be the, so you know at some intermediate time t, your homotopy will give you a path something like this. So this will be f sub t intermediate, okay. F sub 0 is alpha, f sub 1 is beta, alright, and f sub t is something in the middle, alright. And you know all these f sub t's, if you take the initial points, okay, that is going to give you a path, okay, which I can call as gamma. So this gamma of t, gamma of s is just f sub gamma of t is f sub t of 0, okay. And then if I take all the f sub t's of 1, okay, the endpoints of all the f sub t's, that's going to be that's another path, I can call it as delta. So delta of t will be f sub t of 1, okay. Now these are also paths because they are again continuous images of the interval, okay. They are restrictions of this continuous map to suitable subsets here, so they are also paths. Now how do you get the covering homotopy? See, how do you cover this homotopy? So you know you have p here, you have x sub unit. So I do the following thing, you see, for this point I choose a point above, okay, and then I lift this alpha to alpha tilde, okay, but this is alpha tilde starting at this chosen point, okay. Then I also lift this gamma, I will get a gamma tilde, I will get a unique lift, alright. Also I will get I will also get from this point I will get a unique lift of beta, namely beta tilde, and from this point I will get a unique lift of delta, and that will be delta tilde, okay. And the fact is that the endpoint of delta tilde and the endpoint of beta tilde will be the same. That is because actually if you look at this picture, it tells you that alpha followed by delta is fixed endpoint homotopic to gamma followed by beta, okay. This picture itself will tell you that this path alpha followed by delta is FEP homotopic to gamma followed by beta, okay. And since these two paths have the same endpoint, okay, this point above that you get has to be the same, alright, by the very definition of x sub unif, okay. So so the moral of the story, and so the moral of the story is you can lift the homotopy, and in fact similarly this ft will lift to an ft tilde, okay. So the whole homotopy will lift, okay, and one can actually sit down and verify that you get a lifting like this f tilde, okay, and you can check that this lifting is actually continuous, okay. So using this construction you can actually see why this x sub unif has the unique path lifting property and also the homotopy lifting property. And you see further, you see if this was a fixed endpoint homotopy, then this gamma will collapse to a point, delta will collapse to a point, and the unique lift of that will also have to be constant paths above. So what it will tell you is that fixed endpoint homotopies will lift to fixed endpoint homotopies, okay. So these are all things that the covering homotopy theorem in general promises for any you know covering space, but in the case of the universal covering space you can directly see it because of this construction, alright, okay. So fine, so now there is only one more thing that is left, and that is to show that the x sub unif is simply connected. So let us do that. X sub unif is simply connected, I will have to show this. So so for that I am going to do the following thing. So what I will have to do is I will have to take a so I will have to show that the fundamental group at any point is trivial, okay. So but you know the fundamental group at different points are going to be isomorphic, so I can choose any one point and show that the fundamental group at that point is trivial, alright. That is because I have already shown that X sub univ is arcwise connected, okay. So what I will do is I will show that the fundamental group at Cx, okay, is trivial, okay. So what I will do is pi 1 X univ comma Cx is trivial, okay, is a trivial group, okay, right. So so what do? I take a loop here, okay. I take a loop centered at loops starting at Cx and ending at Cx. I will have to show that I can continuously deform it to the constant path at Cx. That's what I have to show, okay. So what I will do, so let me do that. So so let me draw a diagram. Start with the beta in pi 1 X sub unit Cx, okay. So so let me draw a diagram again. So I have this situation, so here is X in capital X, this is P, this is X sub unit, and over the point X in the fiber, I have Cx, okay. And what I have done is I have taken a path beta above, okay. I have taken a path beta above, right, and of course I should take in principle homotopy class, okay, because the fundamental elements of the fundamental group are FEP homotopy classes, right. So I will have to show that this beta is homotopic to the constant path Cx, okay. Now let us project this beta down under P, okay. If you project this beta down under P, what I will get is I will get a path below, I will get a closed loop below, and what is this closed loop? It's just going to be P beta followed by P, okay. It's going to be beta followed by P, alright. And now take this beta followed by P, okay, and take its unique lift to X univ starting at the point Cx, okay, by this construction. Given a path starting at X alpha, I have an alpha tilde, okay. Now this alpha tilde is just the shrinking homotopy, okay, it is gotten by the shrinking homotopy, okay. So you take for this path, you just take the unique lift there, alright. So what will happen is that you will see P circle beta tilde, let this be the unique lift of P circle beta to X sub unit starting at the point Cx, okay. Take this unique lift, alright. Now notice that by the very definition, both this as well as beta, they go to the same element below, alright. So you know P circle beta tilde, if I take P of that, if I take P lower star of that will be equal to P lower star of Cx, P lower star of beta. So I will have to put square brackets. Where you know P lower star is the group homomorphism from the fundamental group above to the fundamental group below, okay. So you know so now I have P circle beta tilde and beta both going to the same thing, but you know that this is injective, okay. This uses the covering homotopy theorem, but in any case we have verified the covering homotopy theorem, namely the important corollaries, namely the unique path lifting property and the homotopy lifting property. So even from that you can show that P lower star is injective, okay. So so what this will tell you is that these two are the same, okay. So let me go back there, yeah. So what, so P lower star injective will tell you that those two elements are the same, okay. It will tell you that these two elements are the same. So what it will tell you is P circle beta tilde is equal to beta, okay. These two are the same. So so what it means is they have to be FEP homotopic, okay. So in particular it means their endpoints are the same. So this will tell you that endpoint of P circle beta tilde will be the endpoint of beta, okay. Now you see you see the endpoint of beta. So see you have the endpoint of beta is Cx, okay. So I will get Cx on this side, okay, and this P circle beta at 1, P circle beta at 1 is actually so what is this P circle beta? So what is P circle beta tilde? You see this is P circle beta, okay, and what is P circle beta tilde? It is the path that I get by shrinking, I just shrink this P circle beta along itself, okay, and that is the path I get above, okay, and this shrinking, okay, at 0 it is the constant path at x, and at 1 it is the path P circle beta itself, alright. So so P circle beta of 1 is actually P circle beta, is just P circle beta homotopy class, okay, because you know for a moment, if you let me again redraw the diagram that I just erased. See, this is x, this is my, if this is my alpha, okay, this is alpha of 1, okay. What is the lift above? The lift above is alpha tilde, okay, and this alpha tilde, which is the lift of alpha, is, how is it given? Alpha tilde at t is just alpha sub t, okay. So you know alpha tilde at 1 will be alpha tilde at t is just alpha sub t, homotopy class of alpha sub t. So you know alpha tilde of 1 is going to be alpha sub 1, okay, but what is alpha sub 1? Alpha sub 1 is just alpha, because you see alpha sub t was defined from I to x by, you know, s going to alpha of ts. So you know alpha sub 1 will be just s going to alpha of s, okay. So this will be just alpha, okay. So you know alpha tilde of 1 is just alpha, so P circle beta tilde of 1 is just P circle beta. But what does this tell you? This tells you the thing on the right is P lower star of the constant path at Cx, okay, and the thing on the left is P lower star of beta, and P lower star being injective, okay, will tell you that this beta has to be equal to the homotopy class of beta is equal to the homotopy class of the constant path at Cx, so that's it. So that tells you that given any element of the fundamental group above, it's homotopic to the constant path. Okay, that means the fundamental group above is trivial, right? And since the space above X univ is arcwise connected, all the fundamental groups at various points are all going to be trivial, and therefore it is simply connected, right? So so again let me repeat what is happening. I will start with a loop based at Cx, I push it down, okay, and then if I take the unique lift of this again to Cx, okay, by the unique lifting property I am going to just get back this, okay, and if I take the endpoints, okay, that is going to tell me that beta can be the homotopy type of beta is the same as the homotopy type of the constant map at this point, okay, and therefore the fundamental group is trivial, okay, that is the whole point, right. Okay, so so that finishes the construction of the universal covering space. What one needs to know is next is the following. One needs to understand why the fundamental group of X can be identified as a subgroup of automorphisms of X subunit, okay. So so this will involve some work.